Hello and welcome to the thrilling conclusion of Pre-Calculus 2-7, Non-Linear Inequalities. This would be day 2. And we're going to start with a conceptual question. We got parabolas. We're graphing them in the plane. Does every parabola cross the x-axis 2 times, or are there other possibilities? Like here we've got this parabola opening down in red. We can see it is hitting the x-axis in 2 spots. But what if I moved it right here? Now it's only hitting at 1 spot. So it is possible to have one x-intercept. It doesn't have to have 2. And with the blue parabola, what if I moved it so far up, it's opening up, we have no x-intercepts. So there are possibilities of 0, 1, or 2 x-intercepts when you're dealing with a parabola. And let's even do a little refresher here. Think about the quadratic formula. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. Remember, the radical, and especially the stuff under it, has a special name. B squared minus 4ac is called the discriminant. And since it's occurring under the radical, let me get a little more room here. If you find this b squared minus 4ac and it is negative, you have no real solutions. So there'll be no x-intercepts. If under that radical, if the b squared minus ac is a positive number, you're going to have 2 real solutions, 2 real x-intercepts. If it's exactly equal to 0, you only have 1 real solution. So the discriminant can tell us quite a bit about what a parabola is going to do, at least in relation to the x-axis. So let's dive into this, example 4, unusual solution sets. Now, we're not going to do them in order. I'm going to look at A and C together kind of as a group. Because if we look at them, x squared plus 2x plus 4, x squared plus 3x plus 5, here everything is adding, everything is positive, and then we've got A is greater than 0, and C is less than 0. So let's look at these. First, let's figure out the discriminant. We've got A, B, C, so our discriminant is b squared minus 4 times A times C. So that's going to be 2 squared is 4 minus 4 times 4 is 16. We don't care what the value is. It's definitely negative. So this one, letter A, has no x-intercepts. No x-intercepts. And it is x squared. It's a positive x squared, so it is a parabola opening up. If our parabola opens up and it never touches the x-axis, it's going to look something like that. So our inequality is greater than 0. So is this inequality, is this parabola above the x-axis? Yes. Does it ever go below the x-axis? Not once. Does it ever even touch the x-axis? No. So for this one, this would be all real numbers. All real numbers are going to make that true. Or you might write negative infinity to positive infinity. Any number that you put in there is going to make that inequality a true statement. Let's compare that to letter C. Let's check the discriminant. B squared is going to be a 9 minus 4, A is 1, times C is 5. So that's going to be 9 minus 20. It's another negative answer, so there are no x-intercepts. In this case, it's also a parabola opening up. It's a positive x squared. So our parabola is going to be up here somewhere, opening up, never touching the x-intercept. But now the big one here is the inequality. This is less than 0. So does this parabola ever go underneath the x-axis? Nope. Not at all, not even for a point. So this would be, the solution set would be, you've probably seen this before, I think Zimmerman shows you this, the null set. That little 0 with a big slash through it, the null set, there are no points that is going to make that inequality true. No matter what number you put in for x, it's never going to be less than 0. So there's our two cases for all real numbers and no real numbers. Because we did not touch the x-axis at all, it was all based on the inequality. Now let's look at this one. Find the solution set of b. So let's see. Let's check our discriminant. B squared is 4 minus 4 times a is 1 times c is 1. So that's 4 minus 4, or 0. So that means we're going to have one point where we actually hit the x-axis. And let's see here. I guess we could factor this one. X squared plus 2x plus 1. That's going to be an x plus 1 quantity squared. So think about when we did shifted graphs. That is going to be a graph shifted to the left 1 unit. We're going to hit here at -1, and our parabola is a positive x squared. It opens up. So now let's really focus in the inequality, less than or equal to 0. So we're asking, does this parabola ever go underneath the x-axis? That would be the less than 0. Or does it even touch the x-axis? That would be the or equal to part. So in this case, we're only hitting at that one point, so that's going to be our solution set. The set of just -1. -1 is going to make that a true inequality. Every other number will come out false. And finally, letter D. Let's see here. If we check our discriminant, b squared would be a 16 minus 4 times a times c. So that's going to be 16 minus 16, or 0. Again, we're only going to hit the x-axis at one point. And if we factor this, we're going to get x minus 2 quantity squared. So that's a shift to the right of 2 units. Here we are at 2. And our parabola, it's a positive x squared, so it opens up. So that's what we're dealing with. And we're looking for strictly greater than 0. So where is this parabola always above the x-axis? Well, it's above the x-axis here. That would go from -infinity to -2. And then we hit the x-axis, and notice there's no or equal to part. So that point is not included at 2. Our next interval will go from 2 to infinity. 2 to infinity. Notice we have in parenthesis there at the, that should be a positive 2. Positive 2. And then 2 to infinity. 2 is not included because that's the one point where we actually touch the x-axis. So there's our odd solution sets. Ooh, and I should point this out. I think letter C, our solution set was a single point. In this case, it's everything except one single point at 2. 2 is the only number excluded. In the last one, -1 was the only number that was in our solution set. Now for a rational inequality. And let's read what the book has first. The concepts of key numbers and test intervals can be extended to rational inequalities. Use the fact that the value of a rational expression can change signs at its zeros, the x values that zeroes out the numerator, and also at its undefined values, the x values for which the denominator zeroes out. These two types of numbers make up the key numbers of our rational inequality. When you're solving one of these, you got to begin by writing the inequality in general form, that is with a 0 on the right and then everything else on the left. So actually this first one here, we're going to kind of jump in. It's kind of deep. We're going to have to do a little work to get this started. So first thing, we're going to move this 3 over by subtraction. 2x minus 7 over x minus 5, and then minus 3 is now less than or equal to 0. And notice I left a gap in there. Before we find our test intervals and our key numbers, we need to get this down to be one fraction. So right now, this is a 3 over 1. So we're going to have to get a common denominator. We're going to multiply our denominator by x minus 5. We're going to multiply our numerator by the same x minus 5. So in our next step, we can have our numerator all over one beautiful denominator, x minus 5. So let's see, first here, that 2x minus 7 is just going to stay at 2x minus 7. Here we're going to distribute, and don't forget the negative. This is a negative 3 to the x, so that's a minus 3x. Negative 3 to negative 5 is a plus 15, less than or equal to 0. Let's combine any like terms that we can. So we've got a 2x and a minus 3x. That's a negative 1x. Minus 7 plus 15 is a plus 8. There's our numerator. And our denominator is x minus 5. Our inequality less than or equal to 0. So that verbal description at the start of this example, it said we find the key numbers by setting the numerator equal to 0. So if we set negative x plus 8 equal to 0, let's add the x to both sides, and we get 8 equals x, or x equals 8. There's one of our key numbers. Now we'll set the denominator equal to 0, x minus 5 equal to 0, and we add 5 and get x equals 5. Now let me point out something here. This inequality is less than or equal to. Remember, we never want our denominator to equal 0. So when it comes to figuring out our number line with parenthesis or brackets, even though this looks like we want a bracket there, because this number came from our denominator, we're never going to want it equal to 0. We're only going to want it less than. So again, keep that in mind when it comes to our number line. Okay, well actually we can just do that part right now. Here's our number line, and we've got a couple key numbers at 5 and 8. I'm going to put 5 here, and I'm going to put 8 here. So let's do some test. Let's find our intervals and test them. So let me make this a little smaller so I have room to work. I'll put this over here. So intervals, interval, did I find the key numbers? I can't remember if I pulled out the 8 and the 5. Yeah, 5 and 8. I had them over there, duh. So we'll go there. Intervals. Interval. We start at negative infinity, and we'll go to the small key number 5, and then we'll go from that 5 to the next key number 8, and then we'll go from 8 off to infinity. Test value. Okay, negative infinity to 5, so that's where 0 is going to fit in. 5 to 8, I used 6 in the past. 7 would also work. And then 8 to infinity, let's use good old reliable 10. And now here, we're going to figure out our sign. And in this case, it is a numerator divided by a denominator. So let's see, 0 goes in, or this right here, 0 plus 8 would be a positive numerator, 0 minus 5 would be a negative denominator, a positive divided by a negative is negative, are negative numbers less than or equal to 0? That would be true. Next up, 5 to 8, if we put 6 in there, the numerator, that would be a negative 6 plus 8. That's negative in the numerator. Downstairs would be a 6 minus 5. 6 minus 5 is positive. Oop, hold the phone. Oh, when I put the 6 in there, negative 6 plus 8, you were probably screaming at your computer. That should also be positive. So that is a positive over positive. That is positive. And are positive numbers less than or equal to 0? No, they are not. That will be false. Last one, 8 to infinity. We're plugging in a 10. So here, negative 10 plus 8 would be negative. And then down in the denominator, 10 minus 5 is positive. Negative divided by positive is negative. And that would make our inequality of less than or equal to 0 true. Okay, number line time. Again, let's make sure the denominator can never equal 0. So this x minus 5, we got our key number x equals 5. We would never use a bracket there. 5 has to have a parenthesis. And actually, it's going to go this way. And then when we get to the last one here, from 8 to infinity, that was true. The less than or equal to, because of the or equal to, we do want a bracket there. So we're going to color in true from negative infinity to 5. So we'll color in this part up to the parenthesis. 5 to 8 was false. It will not be colored in. And then 8 to infinity, our line heads off that way. Again, remember, make sure your denominator can never equal 0. We've sort of overruled the bracket at 8. We have a parenthesis at 5. Oh, and let's see the book's number line there. Yeah, same thing I had. Parenthesis at 5, bracket at 8. So practice problems for you. Ooh, now look here. Let me see. We got 2 of them down here, and that's kind of quite a bit. Let's just do one of those 2. Let's do A. A is a good one because that's got the greater than or equal to. This one just has the greater than. Yeah, so let's just do A here for this one. We might do B in class as an odd problem. So pause the video, figure out these solution sets, and then start it back up and see if you got them right. All right, letter A. Letter A. We could check the discriminant, but that one looks nice to factor. Let's factor it. X plus 3, quantity squared, and it's less than or equal to 0. So if we graph it, the x plus 3, that's a shift to the left, so we're over here at negative 3, and it's a positive x squared, so that opens up. So there's our parabola. Is that parabola ever under the x-axis? Is it ever less than 0 down here with the negative y values? No, not at all. So the solution set there would be the null set. No numbers are ever going to make that true. Letter B, ooh, that also looks like it factors nice. That's an x plus 2, quantity squared. If you check the discriminant on A or B, those discriminants would be 0. And in this case, the plus 2 means we shifted to the left. Here we are at negative 2. Our parabola opens up like this because it's a positive x squared. And in this case, the inequality is less than or equal to 0. Well, the parabola is never less than 0. It never goes underneath, but it's exactly equal to 0 at one point, and that one point is our solution set of 2. Or excuse me, negative 2. Negative 2. We're to the left of the origin. All right, this one, x squared minus 6x plus 9. That's x minus 3, quantity squared. And this one's strictly greater than 0. So if we graph that one, it's a shift to the right. We're here at 3. Positive x squared, our parabola opens up. And now it says strictly greater than 0. So all of the parabola is greater than 0 up here, but there is one point that's exactly equal to 0. So 3 were equal to 0, so that would be the point to exclude. So we could write the set of all x such that x does not equal 3. Or in interval notation, you could write negative infinity to 3 with a parenthesis, and then parenthesis 3 off to infinity. The parenthesis exclude the number 3. Letter D. X squared minus 2x plus 1. That would be an x minus 1 quantity squared, greater than or equal to 0. So our parabola has been shifted to the right 1 unit, so we're at positive 1. Our parabola opens up, and our inequality is greater than 0 or equal to 0. Well, all of the parabola is above the x-axis except for one point at 1, which is equal to 0. So in this case, we would have all real numbers. Any number is a solution to that inequality. Now for this one, again, we're just going to do letter A. So I'm going to keep it down here tucked in a corner. And we're going to start by adding 3 to both sides. X minus 2 over x minus 3. So we're going to add a 3. And again, I'm going to leave a gap in there because now it's greater than or equal to 0. And we need a common denominator. And that's easy enough. We're going to put an x minus 3 downstairs and multiply by an x minus 3 upstairs. So now our inequality, it will have one common denominator, x minus 3. And up in our numerator, we have an x minus 2, and we distribute this 3, plus a 3x minus a 9, greater than or equal to 0. Combine your like terms. Our numerator has an x and a 4, or 3x, that's a 4x. Minus 2 minus 9 is negative 11. Down in our denominator is x minus 3. And our inequality greater than or equal to 0. So it's time to find the key numbers. First, I'll come over here in red ink. Let's set the numerator equal to 0. And to solve that, we will add 11, and then we'll divide by 4. So x equals 11 fourths, that's 2.75. If we set the denominator equal to 0, x minus 3 equal to 0, we get x is 3. So that, on our number line, is going to be a pretty small gap. So here's my number line. Again, 11 over 4, that is 2 3/4, or 2.75. So here on my number line is 2.75. And then over here is 3. That's a pretty tiny gap. I believe in the past I've used 2.9 or 2.8 to see if that's going to work. And let me shrink this up a little bit so it doesn't take up so much room. Okay. First interval, negative infinity to negative 2 3/4, 2.75. I'm going to use good old faithful negative 10. Oop, yeah. Oh, no, it's positive 2.7. Oh, my bad, my bad. So that is negative infinity to positive 2.75. So there we're going to use the 0 test value. And again, our function is 4x minus 11 over x minus 3 greater than 0. So if I plug in 0, the x's disappear, and that'll be a negative 11 over a negative 3. Negative divided by negative is positive. Are positive numbers greater than 0? Yes. True. From the next interval, 2.75 to 3, I used 2.9. If we plug in 2.9, 2.9 times 4 is almost 12. And then 12 minus 11, that's going to be a positive numerator. In our denominator, 2.9 minus 3 is negative. Positive over negative is negative. And our negative number is greater than 0. Well, that's false. So we will not color in that little gap. Finally, we go 3 to infinity. Good number is 10. 4 times 10 minus 11 is a positive numerator. 10 minus 3 is a positive denominator. So that is a positive conclusion, and positive numbers are greater than 0. So that's true. So on our graph, we're going to color in from negative infinity to negative or 275, and from 3 to infinity. Now let's make sure we get our brackets and parentheses right. The number that came from the denominator is 3. You never want that one to equal 0, so that one gets the parenthesis. The numerator 0 is the 2.75. It's okay if your numerator goes to 0, so the 2.75 gets a bracket. And there we go. Is that the end? Yeah, we're going to skip this application problem. Last one here then, example 7, finding the domain of an expression. This is a little different. We got a radical in it, radical 64 minus 4x squared. But remember, we've got a big old rule in math. You never want a negative under the radical. So for the algebraic solution, we can take what is under the radical, just what's under the radical, and say, well, that's always got to be greater than or equal to 0. We don't want a negative under there, but we can square root 0. That's legal. And now let's solve this. The easy way, let's get rid of that negative 4x squared. Let's add it to the other side. So now over here it is a positive 4x squared. Let's divide by 4. So 64 divided by 4 is 16. And that's greater than or equal to x squared. Now I'm going to rewrite this. I just like to have my x squared on the left, and I'll put my 16 on the right. And notice the little alligator here, our inequality, was eating the 16, so it's going to look like that. Now, if we square root both sides, we would have an x here, and then we always do the plus or minus. The square root of 16 is 4. But remember, the plus or minus does not actually occur on that 16 when we square root. Actually, what happens is we get a plus and minus x is less than or equal to 4. And then we could break that into two cases. X is less than or equal to 4, or negative x is less than or equal to 4. Oops. Now, if we divide this second one by a negative, we'll get a positive x and a negative 4, but remember that flips the inequality. So now the little alligator is eating the x. And then we could combine these into one inequality. If I put x in the middle, it's less than or equal to 4. But then it's going to be greater than or equal to negative 4. So there is our compound inequality. And all that work I did to get there, there's kind of a shortcut to it if you think about it this way. So if I go back to this and say, okay, I'm going to square root x squared, that's x, and then I get my plus and minus 4. Just imagine that negative 4 and the positive 4 don't like each other. So the positive 4 is going to stay here. The negative 4 is going to jump over, way over here, and you just get the same inequality, less than or equal to. So x is a number between positive and negative 4. So there's our key numbers. Let's test these out. So key numbers plus and minus 4. So that gives us two key numbers, 3 intervals, negative infinity to negative 4, negative 4 to 4, and 4 to infinity. So we can use our tried and true test values. Get out of there. Negative 10, 0, and positive 10 will work just nice. And let's see, I erased my factored form. Well, we could put it back into the original, 64 minus 4x squared. I guess that wouldn't be too bad. So let's see, if we put negative 10 in for this x, we're going to square that to get 100 times negative 4 is minus 400. 64 minus 400 is negative. But remember, our inequality was greater than or equal to 0. So that's going to be false. Let's plug 0 in for x. So this x becomes 0 squared, which wipes out the 4, and we're just left with the 64. Is 64 greater than or equal to 0? You betcha. True. Oop, I should have wrote positive there. Positive and true. And if we put in the positive 10, 10 squared would be 100, times that 4 would be a minus 400. 64 minus 400 is negative, and that's going to be false. So if we made a number line, negative 4 to 4 was true. And that was greater than or equal to, so we would have brackets at the 4 and negative 4, and the answer would be coming together in between. All right, now let's think about this as a two-dimensional graph. What we started with under our radical was 64 minus 4x squared. So that is a negative 4x squared. So that means our parabola opens down. I don't have a lot of room in here to squeeze in a y-axis, but if we draw it there, our parabola opens down. And remember, we wanted to know where that was greater than or equal to 0. That's where it's above the x-axis. So there's our true interval, and when we go outside that interval, we're now down below the x-axis, which means we'd have a negative under our radical. And we don't want a negative under an even radical. Here's their graphical solution. Yeah, downward opening parabola. It does go through y-intercept there, looks like 8, and it goes down to 4 and negative 4. So from the huddle, we can cancel that one. Do that same song and dance here. It's a little bit different because we have a polynomial under there. It's not an x squared and a constant, but it's going to be the same scenario. Pause the video and then solve this and see if you get it right. Okay, step 1. Take what is under the radical and set it greater than or equal to 0, because we don't want negatives under there. Now this one's going to factor. X minus 2, x minus 5. They multiply to positive 10, add to negative 7. And if we set each of these separately equal to 0, you're going to get x is 2, and you're going to get x is 5. Okay, 2 and 5 are the key numbers. Oop, and I'm going to keep my factored form. There it is. So 2 key numbers means 3 intervals, negative infinity to the low number 2, and then from 2 to 5, and then 5 to infinity. And it looks like we're going to have to use 0 for our test in the first interval. We could use 3, 4, or 5. I think I'll stick with 4. And then 5 to infinity, good old 10. So here, we're going to plug those test values into these two terms and figure out our sign. So we're going to have a couple things multiplied. I'll just set some empty parentheses up. And we plug in 0. 0 in the first one, 0 minus 2 is negative, 0 minus 5 is negative, negative times negative is positive. Are positive numbers greater than or equal to 0? True. Plug in the 4. 4 minus 2 is positive, 4 minus 5 is negative. Positive times negative is negative. Are negative numbers greater than or equal to 0? False. Positive 10. 10 minus 2 is positive, 10 minus 5 is positive. Two positives multiply to a positive. Are positive numbers greater than 0? Yes, indeed. True. So let's do our number line. So we're going from 2 to 5, 2 to 5. Our inequality was greater than or equal to, so we will use brackets. And our false interval, this is the one we're not going to color in. So we're not going to color in 2 to 5, so we're going to go from 2 to negative infinity, and we're going to go from 5 to infinity with brackets at each. Okay, I believe that's the end. Yeah, check WebAssign for the homework, and we'll do some odd problems in class.